Okay, welcome in everyone, and thank you for joining us today for the IES webinar, Improving National Reporting of Greenhouse Emissions Using Atmospheric Observations. So estimating emissions from atmospheric observations is generally a new area of science. Greenhouse and ozone depleting gases are particularly aligned with this practice due to their very nature, long-lived in the atmosphere. Since 2003, the Met Office have been working with the University of Bristol to provide emission estimates. The UK is the first country to report these kinds of results annually as part of their dedication to the UN Framework Convention on Climate Change, with many countries gaining more and more interest as they set out to move towards net zero and to decrease their emissions. Today, we'll be joined by Alistair Manning, who will be discussing his work on comparing top-down and bottom-up emissions and inventories, and how both approaches can work in synergy to gain a better understanding of national emissions. Alistair has worked at the Met Office for many years after his extensive studies of mathematics and a PhD in computing modeling. Their work in the Met Office has always evolved around the area of atmospheric dispersion modeling, but prior to this was focused on air quality and emergency response, and he has been involved in more than 150 publications. As always, there will be a chance for questions at the end of the presentation, so please do feel free to submit these throughout today's talk in the Q&A button at the bottom of your screen. At the end of the webinar, I'll ask these all on your behalf. So thanks again so much for joining, and I'll now hand over to Alistair.
Hello, good afternoon. Hope you can all hear me and see me. So, as Catherine said, I work for the UK Met Office and working with the University of Bristol. I've been involved in the work of funded by the UK government to try and improve the UK's inventory reporting of greenhouse gases. So the majority have got lots of co-workers here. The majority of people who take the measurements, very precise measurements at several locations around the UK. Obviously, without their input, I wouldn't be able to do any work. So many thanks go out to all their hard work. And I'll try and change my slide. Okay, so my talk, briefly, I'll describe how I try and use atmospheric observations to estimate UK greenhouse gas emissions, this kind of top-down view. And then I'll give some examples of the key gases really that we report to the Kyoto Protocol, to the UNFCCC process. I'll first of all show you the atmospheric trends of these gases, how they're doing globally, and then focus in on the UK emissions that we come up with and how by linking with the inventory people, we can use this continual improvement process to try and improve what the UK actually reports. So first of all, I'll start with the method that I use to estimate emissions. So I start with these two key elements that go into an inverse system, which is called. So my inverse system, I've called inversion technique for emission modeling, INTEM. So I take measurements from around the UK, and you can see a slide there of the locations of where the sites are. So there's one on the west coast of Ireland called Mace Head. That's been operating since the 1980s. And that really was the linchpin of starting all this work, really. But then subsequently in 2012 and the next couple of years, we installed more towers around the UK. So there are now 4 towers operating in the UK, and you can see them on within England. They're all on tall telecommunications towers, so they're a good fetch, and they see a large swathe of the UK from each site. Unfortunately, in the summer, you may remember the news, but the most northerly one there, Bilsdale, that unfortunately burnt down. So unfortunately, that is now a historic picture because that tower no longer exists. Hopefully, they're going to rebuild it, and we'll basically start measuring from there in the new year again, but it's on a slightly smaller tower to start with. So that's the measurement side, and the measurements are very precise. They use very sophisticated kit at all the sites. At Tackleston and Mace Head, they've got a piece of kit that we call Medusa, which measures about 40 types of gases, HFCs, CFCs, PFCs, a whole range of gases. At the other sites, we just measure the key gases, methane, nitrous oxide, and carbon dioxide. So that's what's one side of the puzzle. The other side of the puzzle is basically how does the air dilute from where it's emitted to where we take these measurements. And for that, we use an atmospheric transport model. We use the Met Office one, which is why I got involved in the first place. It's called NAME. It's a particle dispersion model. And in this instance, we run it backwards from the measurement site. So we can see where the air has come from, which bits of the surface have influenced that measurement at that time. And you can see the little movie loop going around there. Sometimes we get clean air from the North Atlantic and it swings around and it starts becoming polluted. It becomes more from the UK and Europe. And we take all this information together and we kind of triangulate to where we think the emissions are coming from. So they're the two bits of information you give to the system. You can also give it some prior knowledge as well. So if you're pretty sure you know where emissions are, then you can provide that information to the inverse system as well. Each part of the input components comes with an uncertainty. So there's an uncertainty on every measurements we make. There's obviously an uncertainty on the transport model. You know, is the meteorology correct at that time? Has the dispersion been well understood and modeled by NAME? So those uncertainties are fed into the system as well. Obviously, those are best guess a lot of the time. And they go into the inverse system called INTEM. And out of that comes an emission estimate of the surface emissions. Again, they come out with uncertainties as well. And there's a little map there of the sort of distributions you get out for methane, for instance. So that's the sort of system. So now I want to talk about some of the gases and individually. So we'll start with methane. So first of all, I'm not going to talk about carbon dioxide. Carbon dioxide inversions are very complicated because of the biosphere, the fact that they're changing day to night because emissions and the biosphere is absorbing and emitting on a very high frequency. We've not yet rolled that out into the main system, although there is a lot of ongoing research into how to really verify the anthropogenic component of CO2, which is the key one that people want to know about. But splitting that from the biosphere signal is really difficult. So I won't be talking about CO2, but I'll talk about all the other gases in the what's called the Kyoto basket that are reported to the United Nations Framework Convention on Climate Change. So we'll start with methane, as that's the second most important one. That comes from, its main emission sources are agriculture, cows, basically, waste, landfills, and then you've got energy, leakage from the gas network and the production of gas, and obviously wetlands as well. So this is an idea of the global concentration this plot is showing. So the red line is the baseline that the Northern Hemisphere air that we see at Mace Head. So when the air comes across the North Atlantic and has not really been interfered with by Europe or the UK, I then take an idea of that measurement and smooth it, and you get this trend at Mace Head. So that's the red line. And the blue line is a very similar process that I apply to a site in Tasmania in Australia. So that's very Southern Hemisphere. So you can see the idea of the hemispheric gradient here. The concentration is much lower in the Southern Hemisphere and much higher in the Northern Hemisphere, because that's where most of the emissions are occurring in the Northern Hemisphere. There's normally about an 18-month lag between the Northern Hemisphere and the Southern Hemisphere. And the other thing you can see is that there's a strong seasonal cycle in methane in terms of the concentration, and that's because it reacts with OH. So when OH is high, it knocks it out of it. So there's a summer minima and a winter maxima in both hemispheres. And you can also see very clearly on there that it's growing in the atmosphere, unfortunately, by about 10 parts per million per year. And this growth rate is, this is the growth that we need to change in order to have an impact on the sort of the global greenhouse gas impact of methane. So let's look at some emissions. So when I put the observations into INTEM, I get these emissions out. Let me explain this plot in more detail. So the green line is the green line is the inventory that is reported by the UK government. And you can see that there's been a steep decline. It goes from 1990 to 2 years ago, to 2019. And you can see there's been a steep decline within the inventory from the high levels in 1990 to much lower levels in current day. And then you can compare that with, I've got two two inversions on that plot. So the red is using just two sites. So I've got Macehead on the west coast of Ireland, and I've got a site in the Netherlands as well, which I can put into the system. And that gives me a UK estimate, and that's the red line. And then the blue line is when I've got the full network. So when I've got the other 4 UK sites, plus I've also got Weybourne also operating on the east coast of the UK. So when you've got a much more, much more data, you can go to much more higher frequency, and you get a much tighter uncertainty. So you can see the uncertainty of the blue is much smaller than the uncertainty in the red, where I've only got 2 opposite sites operating. But the key thing you can see there is that at the current time, in the last sort of 10 years, the agreement's been very good. But in the 1990s, there was a very large disagreement. And I've worked very hard with the inventory people to try and understand that. And the most likely cause is emissions from waste that we don't understand. But we've really not really been able to nail that one down. So there's a big disagreement there that we can't really unpick at the moment. But if we look at the current, sort of the last 10 years, sort of from 2012 onwards, when unfortunately the network started at that time. If the network had been started earlier, we might have been able to see more reasons as to where in the UK emissions might have been coming from or not coming from compared to the inventory. But you can see there that the agreement is very good. And you see the uncertainties with the blue line is much shorter, much tighter than the red line. And that's because I've got more measurements as part of the process, which is good. And then you can also go down to a much higher frequency in terms of estimating emissions within the inversion system. And you can go down to monthly inversions. And you can see there that the trend, the black line is the inventory, the red line is the inversion. And you can see both have been declining. The inventory has been declining at sort of 1 to 2% a year. The red line is declining by 2 to 3%, but broadly they're in line. So we're both agreeing that the UK emissions of methane have been declining about 2% per year. But that's also got to be taken into the context of what's happened at the recent COP, where the UK has pledged to reduce its emissions by 30% by the 2030 level, from its 2020 level by 2030. So clearly we've got a lot of work to do by then. So that's methane. The other thing that you can see about, because the measurements obviously really are in real time or only 1 or 2 months behind real time, we can come up with a UK emission estimate which is up to sort of the most recent time. So this goes up to August this year, whereas the inventory is always about 2 years lag behind. So another benefit of the top-down system is that you give you're a year or two, a year to 18 months ahead of the inventory. So that's very useful for the government to have a look-see at what's coming around the line. So let's move on to nitrous oxide. So this lives in the atmosphere for a lot longer than methane. And you can see there, similar sort of trend. The red is the northern hemisphere, the blue is the southern hemisphere. Both hemispheres are increasing and increasing about 1 part per million per year. Again, these are the sorts of lines that need to be flattened and start decreasing if we're going to have an impact on the global warming. So let's look at the UK. And again, very similar sort of plot. The bars represent the inventory in this case, rather than the green line. The blue is when I've only got one site. Very noisy when you've only got one site, and especially when that one site is on the west coast of Ireland, which it predominantly sees because of our prevailing meteorology, obviously air from the North Atlantic. The red is when we've got the full network. So nitrous oxide is predominantly used in the UK. It's following fertilizer application. So it's all about agriculture, and there's a bit about nylon manufacture as well. The big drop in 1998 around here was where abatement, basically limiting the emissions of nitrous oxide from a nylon or an adipic acid plant, which then goes on to make nylon. So if we zoom in over the last 10 years, which is where we've got the best estimates, because we've got the fuller network. Again, the fuller network is in the red, it's much tighter than the blue, wider. And you can see there that actually the top down, the measurement, the INTEM system is estimating larger emissions than are reported by the inventory. Now this is very interesting. I mean, we're trying to understand why this is the case. Are there some missing sources in the inventory that we need to take account of? Because of all these accounting methods, we know how much fertilizer applied to the field, but how much ultimately gets converted into nitrous oxide and where it gets converted is very difficult to assess, which is why the inventory has a larger uncertainty than any other gas for this, and for that reason. So that's nitrous oxide. And then the other thing, again, because we've got the full network, we can do monthly inversion estimates, and you can see the red is the INTEM system. You can see a very strong seasonal cycle in the reported or the estimated emissions from INTEM. And that's because it follows fertilizer application. So when a farmer puts fertilizer on the field and then it subsequently rains, then you get emissions of nitrous oxide, and that's when we see it. So we see, and if you look at the annual seasonal cycle of those emissions, so the red is what INTEM estimates. You can see this beginning of emissions in April, May, June, and July, and then it falls off in the winter months. Whereas the inventory again is just an annual number, so that's another benefit, I suppose, of looking at the measurements as well. You see a real cycle of what's actually happening in reality. So then I'll move on to the next basket of gases, which are called hydrofluorocarbons. Now there's a whole suite of these gases of decreasing importance that are reported every year. HFC 134A is the most important. That is the one that people use in their cars, their air conditioning in their cars. There's also general refrigeration gases, blends of gases of HFC 125, HFC 143A. Basically, this is a carbon, links of carbon surrounded by fluorines and hydrogens. All of the chlorine has been removed from these compounds. So these compounds came to become important because they are basically the follow-on from CFCs. So it started off in CFCs in the 1990s. They were phased out through the Montreal Protocol. We moved on to what's called hydrochlorofluorocarbons, HCFCs, which have got a little bit of chlorine in. And then we've moved to these HFCs where it's got no chlorine at all. So in terms of a Montreal Protocol, i.e. impact on stratospheric ozone, they have no influence, but clearly they still have well, not clearly, but they do still have a global warming potential. I mean, CFCs had an even larger global warming potential. So that was a double win to move away from CFCs, both from an ozone, stratospheric ozone perspective, but also from a global warming perspective. If you look at the Northern Hemisphere concentrations here, very similar thing is happening in the Southern Hemisphere as well, but I thought we'd put them all on two plots effectively, and you can see that since the move away from CFCs and move to HFCs, obviously the concentrations of these gases are growing in the atmosphere very strongly, and virtually all of them, especially the top four, have been growing very strongly and are continuing to do so. Although there is UK legislation and European legislation that came into force in 2017 called the F-gas regulation, which means that we're moving away from using these F-gases as much within our society. So we're moving towards HFOs, which potentially have other issues, but we won't talk about them just yet. So in terms of UK emissions, where are we? So when I do the inversions per gas, so I do an inversion for HFC 134A, and I'll show a quick example of that in the next slide. I also do a separate one for 125, etc. And I put them all together based on their global warming potential. And you come up with this combined picture for the United Kingdom. So the bars are the current inventory that was reported in April this year. The green line is what was reported the previous year. So you can see there's been a change in the reported emissions. And I'll talk about that towards the end of the talk as well. And then you've got two INTEM lines on there. So one where I've done the inversion over a 2-year period, and that's the blue line. So that's more smoothed out of what's going on. And then I also done a 1-year inversion as well. And you can see that the agreement is reasonably good. The inventory is higher than INTEM in this case. But the interesting thing is also the impact of that legislation I was just talking about, where policy, i.e. imposing a change that industry can use, they switched away from using these HFCs within the UK following that policy. And from 2018 onwards, there's been a decline of these gases. So that would be an indication of a success of a policy that's been implemented by the UK government and Europe. It's interesting that the inventory is not showing as big a decline. So it thought the impact of that policy would be much slower than it seems to be by looking at the measurements. So that's a real interesting finding, and it maybe mean that the inventory needs to reassess how quickly people or how industry is changing, how quickly industry is changing to adapt to these new policies. So let me just go into one of those gases in more detail. So 134A, this is the most important one because it's the one with the largest concentration. And you can see again, you've got the Northern Hemisphere in red and the Southern Hemisphere in blue, and you can see that it's still growing strongly in the atmosphere. There is a slight decline at the end if you're looking at the last year or so, in terms of it slowing down rather than declining. So that's the global, but obviously all these gases need to be flattened out if we're going to start achieving global warming targets. So in the UK, just looking at this particular gas, and you can see the inventory is the black bars. The green line is the inventory from last year rather than this year. So obviously they reworked the model they used within the inventory. And you can see our estimates, and our estimates are, you know, they're showing this sharp decline from 2018 to the subsequent 2 years, 2019 and 2020. So that's, and we would think that this is an impact of the policy of them moving away from using 134A in cars, for instance. So, and then the other thing you get with these inverse systems is a distribution. So you get a map of where you think the emissions are coming from. So, and in this case, the inversion moves towards thinking that everything is very population weighted, which for 134A, because it's largely in cars, it's also used as a propellant as well, but all very used by people effectively. So where people are, you get emissions of 134A. It's mainly used as at use rather than its production, i.e. people driving around, their AC might be leaking slightly in their cars, or when their AC gets changed, etc. at the garage. So you can see you would expect it to be broadly population weighted, and the inversion comes out with saying it is broadly population weighted. So there's no real surprise there. So that's good. No. So now we're talking about perfluorocarbon. So this is when you've literally got no hydrogens on your carbon. So there's links of carbons surrounded by fluorines. And there are 4 principal gases that are reported as part of the UNFCCC reporting process. The most important of this is PFC-14. They've got a range of different uses. They're produced as a sort of a byproduct for aluminium and semiconductor production. So they're really a waste, but also they're used in semiconductor to drill holes in the wafers as well. And they're also used for producing non-stick frying pans, etc. So there's a whole raft of uses for these particular gases, but mainly it's in aluminium and semiconductor processes. And you can see, as with all the other gases, they're all rising in the atmosphere, and this is the Northern Hemisphere, and they live in the atmosphere for a long, long time. PFC-14 will live in the atmosphere for 50,000 years. So it's going to be around for forever. Effectively, so we really ought to be trying to prevent that being emitted. When you look at the UK emission estimates of all, again, I've done this kind of composite, I've done individual inversions of all these gases, and then I've added them all together based on their global warming potential, and then you get this UK composite idea. So again, the black bars are the inventory. The green is last year's inventory, so there's been no change in the inventory between the 2 years, unlike the HFC's example before. And you get these 2 different inversion systems. The blue line is a 2-year inversion, so it's more smoothed, and the red line is more a year-to-year inversion. And you can see the agreement, it's largely pretty good, although there's some interesting variability in the inventory, which we don't particularly see within the inversion system. So if we just look at one of those particular gases, because it's quite interesting in terms of a UK perspective, this is PFC 218. It's used in electronics, making of electronics. And there's actually a factory that makes this product near Preston. And we started, so the inversion starts off with an absolutely flat map. So we don't give it any information about where this factory might be. And the inversion then produces this result, which clearly indicates within the last 8 years in this case, that the emissions have been predominantly from the northwest of the UK. We're only measuring at 2 sites within the UK here, well, not 2 sites in the UK, one on the west coast of Ireland and one in Norfolk. There were 2 other sites in Europe, but they're obviously a long way away, so they don't really give much information about the UK. And you can see that there, it pinpoints largely the where he thinks the emissions are coming from, and it's the northwest. And we know that's the main source of 218 within Europe. They export this canisters of gas to the Far East largely for use in the electronics industry. So that, again, it's a very different distribution than you saw for 134A. So the inversion is obviously doing something different on a gas by gas basis, which is obviously very good to see. So I'll finish, obviously that very significant source near Preston. And I'll finish with one last gas, SF6. So this is used in high voltage switchgear. It's got a very, very high global warming potential of 23,000 times that of CO2. So really, really an important gas that needs to be controlled. And it's growing very strongly in the atmosphere, like all of the gases I've been talking about. So again, that needs to be changed. In the UK perspective, the agreement between the inventory and the top down, especially when you've got more measurements, either full network operating, you can see that the agreement is pretty good. The red line and the black bars, agree pretty good. So that's good to see. It's interesting when you look at the distribution. Again, we start with completely flat land-based emission, and it comes up with this. And clearly, there's a very large source in southern Germany. And when we've investigated this and talked to people in Germany, there is actually a manufacturer who manufactures high voltage switchgear in southern Germany, and that seems to be where most of the emissions in Europe come from. So that's something that we can pursue with German colleagues. So that's SF6. So let me talk now about the process of how the top down, the interim estimates feed into the whole inventory and accounting system. So the inventory is created by effectively having activity data, i.e. for instance, for methane, you would count the number of cows in the UK, and then you would have an emission factor. So for each dairy cow, you'd say, how many dairy cows we've got in the UK? We know how much, or we think we know how much emission comes from each dairy cow, and we'll just multiply those together in a big Excel spreadsheet. And they do that for all the different types of cows, but also different types of landfill, different types of, or how long are the pipes in the gas distribution network, etc. And they have emission factors, what gets leaked out per unit activity, and then you've got activity data, and they just multiply those two numbers together and add them all up. That's the basis of the inventory, and they do that for all the different gases. It's a very complex system in terms of the amount of data they have to collect across the whole of the industry and agriculture, etc. So that's how they every year come up with an annual UK estimate as part of the process of feeding into the United Nations Framework Convention on Climate Change, part of our requirement as we've signed up to that process. But it's always 2 years behind. So in 2021, in April 2021, they will have submitted their estimate up to and including 2019. So they'll redo every year from 1990 all the way through to 2019. So they can improve what they do previously as well. So where we come in, obviously, I've just showed you what we do. We Intem estimates UK emissions, and it's completely independent of the reported inventory. So that's really the key point here. 2 different methods are trying to do it in 2 different ways. How do they compare? Some of the gases compare well. Some of the gases, there's some disagreement. So that's the So that's what we do. We compare the two systems and we feed that back. So I feed that back to the inventory compilers in the UK, who are also funded by UK government. And we work together to understand why those discrepancies might have occurred, and therefore on this kind of annual cycle basis, continually improve the UK inventory. So just an example of how that works in practice. So I kind of alluded to this earlier. So the UK HFC emissions in the 2020 inventory was this green line. That's what they reported as a composite of all the HFCs. We came along with the interim estimates and produced that line, and you can see there's a big sort of discrepancy between the two. The UK government then went to the industry experts and showed them this, and they reworked their inventory model. They came up with different activity data, different emission factors by going back to industry and trying to work out what was going on. So then they came up with a different inventory model, and now they came back with the black lines, which obviously are much closer, and certainly in the earlier years, to what the atmosphere is seeing. So that's how this process works. So there's still some work to do, especially in the latter year, where in 2019 they're not seeing the sharp drop that we're seeing in the within the atmosphere. But it's that continual process of working together. So just some concluding remarks then about what, just to remind you what I've just been going through. So atmospheric observations of greenhouse gases are used within an inverse system, linking together an atmospheric dispersion model and atmospheric measurements to come up with a UK estimate of emissions. And we compare that to the inventory, and we use this in this cyclic process to try and improve what the UK submits to the United Nations Framework Convention on Climate Change. And we've done this every year. The first time I did this was in 2003, and we've been doing this every year. And say the UK was the first country to start doing this. Two other countries have come on board since then. So Switzerland and Australia now do this routinely, and Germany and South Korea and several other countries are also now building up the process of doing that. And this is because it's seen as a very good way to understand your emissions and to understand whether the policies you're implementing are having an impact on the actual emissions rather than just on a piece of paper. Because industry might think they're doing something, and they might think they're reducing their emissions, but what's actually is the atmosphere seeing is really ultimately is the most important thing. So if the atmosphere doesn't see it, then clearly there's more work to be done. And a lot of this work that I've been talking about today, certainly on the HFC part of it, but in terms of the whole INTEM setup and how we do the inverse system, is all within that paper that was published earlier this year. And the key thing about this is it's all funded by the UK government, both the inventory aspect, but also the work that I do. So we work very closely, all three parties, BEIS, also the inventory people and ourselves, to try and come up with every year a better product and a better understanding of emissions, which then BEIS can feed back to their policy people that will ultimately affect policy going forward in time. So with that, I will stop talking. Thank you very much.
Wonderful. Thank you so much, Alistair. That was very interesting. We've got lots of questions, so we can probably just jump right in if that's okay.
Go for it.
Let me
Yeah.
just stop the sharing so they can see us. Perfect. So the first one is, how are you measuring CH4? Might your method suffer from cross-response and actually responding to other gases?
So I'm not a measurement person, so I'll first of all get that on the table. I'm a modeler, so I'd have to really refer to my colleagues at the University of Bristol, but I will try and give a stab. So we use this instrument called, it's called a Medusa, as I said before, and that it's all about gas chromatography. And they try and separate, they pre-concentrate, so they collect the gas over a 2-hour period, they pre-concentrate, and then they send it to a gas chromatography and look for peaks within the gas chromatography. And it's the size of that peak which we let then, through calibration, they can say how much is in the atmosphere based on that calibration of so it's the size of the peak. So it's probably not a very complete answer, but that's probably as far as I'd like to go.
Perfect. So the next question is, well, first of all, they started with thank you, very good presentation. What are the CO2e emissions of waste, and what source is best for you to get this data? What are the CO2e emissions of EFW incinerator plants?
Okay, so yeah, so emissions are from landfills. So what they do now is they cap landfills and they drain off the methane and then generate. So some of it gets leaked to the atmosphere, which is what we see as landfill, and some gets generated into electricity. So how they come up with their emission factors for their use and the activity data for landfills is very complicated, because really what you need to know is what goes into the landfill to know how much methane it's going to produce, therefore how much is going to leak out, and also you've got to subtract from that how much you've used to generate electricity. So again, that's really an inventory question you're asking me, and I would have to refer to my colleagues in the inventory team as to how actually they come up with that. But again, it's quite a complex process. They've done lots of measurements around landfills to try and come up with their best estimate of what their emission factors are. But the key limitation of any landfill is the activity data, because they don't really know what's going into them on a basis. So they have to do it on a very averaged annual estimate. So it's quite uncertain. That's quite an uncertain part of the inventory. That helps.
Great. So the next one is, I wanted to know about the major challenges associated with UK's national GHG emission measurement and verification.
Okay, the biggest challenges. Well, the biggest challenge is coming up with the number for CO2, I would say, and that's because of this, as I said in the talk, this diurnal emission and sink of CO2 within the atmosphere. So if you look at a measurement of CO2 on a diurnal cycle, you can see it going up and down like a yo-yo, day to night, and that's because obviously the biosphere is absorbing during the day, and obviously summer to winter you get a big change as well. So that's the next big challenge, because CO2 is 80% of the UK's inventory, and obviously understanding, but there again the UK government would say they would have a very good handle on their the emissions from fossil fuels, because they know how much fossil fuel is sold in the UK largely. So there are some uncertainties associated with that, but very small. It's the uncertainties are much larger in, say, nitrous oxide for fertilizer application, because that's a chemical and biological process to convert it into nitrous oxide. That's a lot more complicated to do and much larger uncertainties. So I think CO2 is the really next big challenge. And then the other challenge within sort of the current work we've got is the atmospheric transport modeling. Is how well does the model represent dilution from emission source to where it's measured. And the key thing is what we don't have is actually a really good testbed case. We've never had an example of where something's been released that we know exactly what's being released to measure it 500 miles away at a very small concentration over a long period of time. There has been obviously some small experiments where this has been done, but not on a systematic way that you can test whether your transport model is doing a really good job. And that's a really, that is an area of real challenge, I think.
So the next question, is it possible to get a figure for the total IR absorbance of the atmosphere? And does this suggest any other gases which might be absorbing IR and heating the planet? I know you have not mentioned water vapor, for instance.
Okay, this is completely outside my comfort zone. I don't know. So all the time so the measurement people are always looking for different compounds that are growing in the atmosphere. But how they actually then work out the IR and whether that one is an important contribution to global warming, I don't know. I would have to say that that's just too far from my area of expertise. I do apologize.
Fair enough. Someone's asked, could this method be applied to ammonia?
Yeah. Well, ammonia is, again, like CO2, complicated because it's emitted, it's deposited, there's chemistry. So yes, but the modeling would have to be more sophisticated and tuned specifically for ammonia. So we are starting to do these sorts of processes on So what comes after the HFCs, as I've said, there's been this switch away from HFC 134A to HFOs. HFOs have got a very short lifetime in terms of days. So therefore you have to feed in the idea of OH sinks and atmospheric chemistry. So we're starting to do that, and that's where ammonia could start to be addressed. There's also the idea of hydrogen as well, which is also very similar, simpler than ammonia, but still complicated because there's a sink, there's a soil sink, there's obviously a direct emission, and obviously switch to the hydrogen economy. It's going to become more important to know these things, but also there's a chemistry production of hydrogen and the chemistry loss of hydrogen. So ammonia is complicated because it's also dealt with by rainfall as well. So ammonia is complicated. I would say that we're not really ready to do ammonia on this sort of scale, I don't think. Certainly on a national scale, no.
I also see that Andy, who asked this question, there's a message from Peter with a email of someone who might be able to help you with that question as well. So thank you for providing that. Amazing. So the next one is, have you tried using this method for NOx emissions, NOx emissions?
I haven't. Well, not for many, many years. Again, you've got the complexity of atmospheric chemistry that's going on. So you could do it to NOx better than NO2 or NO, for instance, obviously because there's the interplay between those two gases. So you could do it with NOx, but you would have to have an idea of loss rate, because obviously when you're emitted, when your NOx is emitted, either as NO or NO2, then it then goes through the atmosphere, and any loss process that occurs between when it's emitted and when you measure, you have to model that. So the question is whether you can model that well enough. If you can model that well enough, then you could apply this system to it, definitely. So that is something that could be done, because there is very good modeling of NOx in the atmosphere. So again, it's really about, can you understand the dilution from emission to where it's the receptor where it's measured? And if you can do that, then you can apply this system, yes.
Great. So I'm just going to finish with the last two questions and then we'll end. So the next one is, presumably we can improve on the error margins by increasing the number of observing towers that you have. Are there prospects for doing this?
There are. Obviously, the loss of Bilsdale being burned down was obviously a big blow to the system. There is hopefully going to be a new tower in Scotland near Dundee. The Bilsdale Tower will hopefully be rebuilt. It'll start off smaller as a temporary tower and then hopefully go back up to its original 300 meters. So there is potential. We're also exploring whether we could put one on, say, Jodrell Bank and places like that. So there is potential for doing this, but it's quite complicated and costly to do that. But obviously, the more measurements you had of these gases, the much better understanding of the spatial and temporal resolution that I can go down to. So absolutely right. The more measurements, the better this system is by far.
Great. So the last question is, would having more measurement sites in the UK allow you to improve the spatial resolution of the model estimates, or is there already optimum for this methodology? So I suppose a very similar question.
Yeah, well, I mean, you're never optimal in the sense, it depends what you want to achieve. Again, this is a question that always comes down to, in terms of a UK number, we're probably okay-ish on the low side. I think another site that measures all the F gases and PFCs in northern England, so Scotland, would be much better. That would close the gap. So on an annual national basis, that works quite well. For gases like nitrous oxide and methane, where you've got certainly for nitrous oxide, where you've got this strong seasonal cycle, spatially varying emissions, and for CO2 in a similar vein, you'd need more measurements to drill down sufficiently to be able to say what sort of process is causing these emissions. So separating landfill emissions of methane from gas distribution and agriculture, you need more measurements to really start to split those down, or you start using isotopes, or a combination of the two. Isotopes are good because you can start to separate those different sectors, and those sectors are the ones which are really important to the UK government. So if I could come up with this is the agricultural part of UK methane, that would be more useful than coming up with a total methane number. So more measurements will allow that greater sectoralization of the emission estimates that I come up with. So no, we haven't reached the optimum. But it also depends really on what question you want to ask, I think.
Great. Well, thank you once again, Alistair, for that amazing webinar. I think we all learned a lot. There's some really nice comments in the chat saying how much they enjoyed today. So thank you again. So that's it for us today, attendees. Thank you for joining us. I hope you enjoyed it and found this webinar informational and beneficial. So this webinar has been recorded and will be available on our IES website and the YouTube channel. If you are watching this on YouTube, please do subscribe to our channel, like this video, and hit that notification bell to gain notification of new content. Thank you again, and thank you, Alistair. Again, this was really great, and have a wonderful afternoon, everybody. Goodbye for now.